Okay, the problem set assigned this week is so you can learn to do method of sections. And really, there is no necessity very often. That's why I use method of sections to solve for the reactions. But I want to point out on these problems, one of the things you're supposed to do almost innately, unless you're, extremely in a hurry and you don't want to have a check, is you need to solve for reactions. And you do that by adding up. You need to add up the number of reactions to decide, can you solve for the reactions? Now, you'll see if you have three unknowns and three equations, meaning some of the forces in the x, some of the forces in the y, and some of the moments, then you can solve it. Yes, you can. Sometimes you will have 4 or 5 unknowns and 3 equations. Can you solve it? Probably. But you need more equations or more relationships. So very often those relationships can come from the geometry. The relationships come from either the geometry. In other words, you know the direction. So if you know that, then you know that somehow this tangent of that angle is going to relate those two components. They also may come from the material, or that famous PL over AE equals that delta length. So it can come from material or boundary conditions. All right, so the first problem in this week is 3.18, and if you notice there, you actually have 2 pin joints, which would mean 4 unknowns, and that ostensibly cannot be solved. So again, I'm going to remind you the best way is to just come and think about that as being force times orthogonal distance. So for solving the reactions, I'll see if I can sketch this here. Remember, sketch the scale. I've got a pin joint there, a pin joint there. I have a long axis here that's about that same distance between. Goes down to there. Of course, that is not in the structure, but we're going to have a line that looks like that and a line that looks like that. Comes down. Right, that structure is there. You have what's called a truss. Right, now these are only 3 deep. This isn't quite sketched that well. Right, and they're trying to get you to solve for this, this, and this. In all reality, I'm sorry, not that. These 2, 3 here. Let me see if I can get my pen out and erase just this line. I can. All right, so they're trying to get you to solve for these 3 unknowns. And if you think about it, you are given a force here of 4, 4, and 2. And I continue to very much encourage you to look at these problems as something you should be able to get pretty close to without even picking up a pencil, by essentially saying this. When you solve for do your problem here, you have to replace this with 2 unknown forces for which you do not know any relationship, because you have a couple of these members here. And this one is 2 forces for which you do, however, because of the geometry of this. This here, since it has 1 truss coming in it, truss members can only be tension or compression. They can't be anything else. So all of a sudden you know that there is a 6 to 3 relationship. You know that this is 6 this way and 3 that way. So you know that 3 times the reaction at A and the X, okay, equals, let's see how that works. So we have basically, that's 3 to 6 basically. So you know your reaction in the x is going to be 6 times reaction at A and the y. In other words, if you look at 3 and 6 here, that's kind of a a 1/2 relationship. And what you probably see there is you probably start to see this being a 2, a 1, and a square root of 5 relationship here. However, flipped around. But that relationship here is the one that allows you to solve this by sum of the moments about B. And so we're going to go ahead and solve that just like we did a second ago. I would not recommend it. I would recommend you doing it by force times orthogonal distance, or by R cross F. But in these problems, basically the reactions are best solved by force times orthogonal distance. So I've got B here, and I've got A here, and let's go about solving those reactions. And so we have the sum of the moments about B. You have to realize, right, writing the sum of the moments about B, you're going to solve for the reactions at A. You're going to have two equations. One is, we're going to start with going around the pike. Reaction at B in the x times distance, which we said was 6, and you remember now that is going in a negative direction. I tend to tell you it's probably, once you draw your vectors in the way you're assuming them to go, tension or positive typically, you're best then putting down the force, putting down the direction, then deciding in which moment direction that shown vector is spinning. If you get a negative, you'll just go the other way. So you have the reaction at B in the x times 6, and it's negative because your thumb goes into the board with your right hand. And then you have 4, the first 4, it's 6 away, it is also negative. And then you have another 4 times 12 away, it is also negative. And then you have another 2 times 18 away, and it is also negative. And so in actuality, you don't need the other equation here. You can solve for the reaction at B in the x. I'm sorry, the reaction at A, got that wrong. It's the reaction at A in the x. Remember, you're taking two hockey players out of the game because they're actually standing on the same spot here. So there's, just to give you that analogy. So right here, you solve for the reaction at A in the x. Reaction at A in the x is going to be equal to all of this, right, divided by 6. So I'm going to pause here and do some calculator punching. And that turns out to be a negative 18. And remember, we show our reactions positively, and so we know this is a negative 18 going this way. Which means that we know that the y component, because we had this relationship of the y component being half the x component, the reaction at A and the y equals 9. So now we have our reactions here. You see on this structure, and you don't want to necessarily slide into this, on this structure here, you have to now know that the reaction at B in the x has to be 18, because it has to be an equal and opposite, because you have no other forces along the x direction here. And you know the reaction at B in the y should be equal to 1. The reason why that is, once again, is because of the fact that the sum of the forces on the whole structure has to be equal to 0. However, what you would more correctly do is pick a spinny point up here and do the same problem again. So let me do that real quick. Just, you know this is true, but you went the wrong way to get it. And you'll do that very often in a structure. You should have some other checks involved as well, but we're going to now write the sum of the moments about A the same way. We're going to go around the pike, I guess. We'll go for the 2 this time. We'll start on the end. 2. It is 18. In other words, you're looking at the distance, the moment arm here, right? 2 times 18, and it is in a negative direction. We have 4 times 12 in a negative direction. We have 4 times 6 in a negative direction. And then we see the reaction at B in the y does not have any moment arm. And then we have the reaction at B in the x is in a positive direction and it is 6 away. And so we can solve for the reaction at B and the x, and we will get 18. So that's how you go about doing the reactions, by breaking vectors into components. In many ways, I guess sometimes that will be easier, but it's going to kind of tend to keep you in that sum of the forces, which isn't always the most efficient when you're trying to really think correctly